Alright, in another classic scenario, we've got a simply supported beam, a uniform beam, and a uniformly distributed load. That's your typical floor beam in the design context. Right? W is positive downwards, so when we go to apply our model for beam deflections, right, that would be the second derivative of the curvature is equal to the load. We have to recognize at some point here Q has been defined as positive upwards, so Q is equal to then the opposite of W being positive downwards. Something to keep in mind as we do all this work and then we compare later. We're going to do all this symbolically because it's a lot easier to do symbolically than it is to put all the numbers in, keep track of all the units all the way along the length. Right? Let's set up our coordinate system here that our origin is over to the left. Right? That means that with our simple support here that our moment at x equal to 0 is 0, our transverse displacement is equal to 0, and then over here at L, then our moment again is 0 for the roller support, and a transverse displacement is 0 as well. Right? So we're going to go find what the deflected shape of the beam equation is. We're going to find its maximum deflection. Hey, you know, symmetric situation, we would anticipate we'd get that to be at the middle, and that will turn out to be the case here. And we're going to do this entirely symbolically here. Right? So we're going to find the shear and the moment diagrams and write their associated functions. Now, we know, without having to dawdle around with this too much, exactly what's going to happen here. Right? The shear diagram is going to go up by the reaction at the left, so that'll be WL over 2, W being positive now, downwards it is, and then we've got the reaction at the left will be also upwards at WL over 2, so the shear is minus WL over 2, and we've got then this little guy, right? Well, wait a minute, we got to somehow find a way to get the shear function out of all that, right? You could have started with, well, V of x is equal to the integral of Q dx, and Q is a minus W, so you would have had minus WX plus your first constant of integration. Right? Now, technically we don't know what the shear is right here, but since we actually do know it, we could evaluate for C1, and at x equal to 0, V is supposed to be WL over 2. So that actually tells us that's minus WX plus WL over 2 in the end. I mean, we're not really cheating, but that's not strictly how you solve for these things. But note, it is an equation of a straight line. If we put x equal to L, we get minus WL plus WL over 2 or negative WL over 2. So this equation is correct. Right? There's nothing wrong with the actual equation that we ended up with. Right? Then we got to go get the moment function. Right? Now we've done this one a number of times. We know that this thing is a second order curve. It starts at 0, ends at 0, ends up with a maximum right at the middle of WL squared over 8. That's your moment diagram, but we're going to actually need that function. So our moment here is the integral of our shear. So that's the integral of minus WX plus WL over 2. Integrating with respect to x, we get minus WX squared over 2 plus WL over 2 times x plus our second constant of integration. Now, normally we really would have had plus C1x. Oh, this was C1 right here. Right? And we would have gone and we would have said, okay, the moment at x equal to 0 is 0, and we would have had, oh, 0, 0, this would have been C1x plus C2 has to be equal to 0, and we would have found out, bam, that's gone. And then we would have come back and we would have evaluated the moment at x equal to L. Well, that's minus L squared over 2 plus C1 times L has to be equal to 0, and we would have gotten to this answer right here. That's how you would have actually done this in a proper way. Right, or a formal way. So we end up with a moment function, though, ultimately, that I couldn't have written it by observation. I would have had to go do this. minus wx squared over 2 plus wl over 2 times x, and of course c2 is equal to 0 here. All right, it seems like every example we've done that one of those constants has turned out to be 0. It's not always going to be like that. It just is this time. All right, so that's our moment function. And we know that that's entirely positive, and with the boundary conditions being what they are, then with positive bending moment we've got positive curvature or smiley face everywhere. So this is easy to draw the elastic deflected shape. Bam, there you go. There's your little v of x. Right? We've got, again, oops, v at x equal to 0 is equal to 0, and v at x equal to L is also equal to 0. Alright, now, we're just going to turn the calculus crank down. I mean, it's just the same old thing over and over and over here. Our curvature is the moment divided by EI. And that then is our minus wx squared over 2 plus wl over 2 times x. Now, I just want to check something real quick here. At x equal to L over 2, what would I get? WL squared over 4 here. That'd be a 1/4. I get WL squared over 4, that'd be 1/8. Minus 1/8 plus 1/4 is a plus 1/8. So the maximum moment would be WL squared over 8, which is what I claimed that it was. Bam, right at the middle, right there. Okay, so that was good. Just checking everything, making sure it all is going to work out, because we're doing a heck of a lot of work here, and I want to catch mistakes as soon as I can find them. All right, theta equals the integral of kappa dx equals then the integral of 1 over EI, which gets pulled out as a constant. Do I have to actually do all this work? Yes, you do. Well, can't I just put it in a symbolic operator? Well, yeah, if you know how to do that right. And frankly, what the symbolic operators usually get wrong are those constants. You got to make sure it brings out the constants for you. Oh, come on, that can't be that big a deal. Oh, yes, it is. You want to hear me get pretty excited about that, go back to a previous video. Alright, so there's our slope. I think that's integrated right. X squared becomes x cubed. We get the 6 in there, 3 times 2. This one becomes an x squared over 2 times 2, or 4, plus the c3. I got no slope boundary conditions. Yes, I think the slope is 0 at the maximum, or at the middle, but I can't, that's not a boundary condition, doggone it. Don't use it as such. I have to go and integrate this one more time. Do I have to write all this out? Yes. Why? Why wouldn't you? It's fun. You're mean. I'm a professor, of course I'm mean. Right, again, constant integration there that we've got to have to make this all work. Alright. Wow. Are you exhausted yet? I'm not quite exhausted, but I'm getting tired. There's a lot of work. Now we got to evaluate those two. But note, at x equal to 0, v equals 0, we evaluate all that, and that's going to tell us that c4 is equal to 0. Right? So at x equal to L, then v is equal to 0 also. What's that going to tell us? Right? So the EI is going to go away when we solve in here, and we're going to have x equal to L. We've got minus WL to the 4th over 24 plus WL to the 4th over 12 plus C3x, and that's all got to be equal to 0. So therefore C3 will equal some W times L cubed over, well, that's minus 1 over 24 plus 1/12 is going to be a plus 1 over 24, which we take it to the other side, and we'll get that. So our function for our displacement is 1 over EI minus WX to the 4th over 24 plus WLX cubed over 12 minus WL cubed over 24 times X. Right, now one thing I want to check are units. I get length to the 4th, XL cubed. LX cubed is length to the 4th, and X to the 4th is, of course, length cubed. That's all the same. W has force per length, so force over length times L cubed would be force length cubed over force length squared, right? Force over length squared would be E and times L to the 4th, so that's all FL squared. So FL cubed over FL squared will give me length. That's exactly what it should be. Right? Now before we go on, let's just even check this with another version of all this. And you come along and you see here, simply supported beam, distributed load, W positive downwards, we get V equal to minus WX over 24 EI. There's your L cubed, there's your minus 2 over 24, which would be 1 over 12. Right? A minus times a minus, that would make that middle one positive, so on and so forth. In other words, this expression is identical. Same W, same meaning of W, positive downwards. Right? Now, if you looked in there, you saw that we also had the answer for the max displacement, which is 5WL to the 4th over 384 EI. I use it so often, I know it. Theta equals 0 is going to be found from setting all of this, evaluated at some sort of unknown x, equal to 0, so the EI goes away, so we minus WX cubed over 6 plus WLX squared over 4 plus our C3, which we found to be minus WL cubed over 24 equal to 0. Isn't that interesting, right? So minus WX cubed over 6 plus WLX squared over 4 is now equal to WL cubed over 24. Well, the W goes away, doesn't it? Yeah, the W goes away. And so what you're going to find when you solve this, there's a lot of ways to solve it, but you're going to find out that X is going to be equal to L over 2. Right? And so the L is easy to see. We get an L squared, that's L cubed here, bam, they all go away. So that leaves us with a 1/2, which becomes a 1 squared, becomes a 1/4, so that's 1 over 16. And then 1 over 16, this becomes a 1 over 8. 8 times 6 is 48, and 16 goes into 48 3 times, right? Pretty sure. 48 divided by 16, yep, 3 times, and we're going to get this 1 over 24th out of all that mess, right? Even prove it, right? Minus 1 over 48 plus 1 over 16, and 3 times, that'd be 3 over 48. 3 over 48 minus 1 over 48 is 2 over 48, and that's a plus 1 over 24, so there you go. It really is. There's your solution for that particular one. There's other roots, but that's the primary root that has any relevance, right? Put that back in to here, and you'll find out that our delta max at the middle is 5WL to the 4th over 384 EI. Of course, that's really technically a minus going downwards, right?